we continue the discussion on the Primal-Dual algorithm. In the last lecture, we were solving this problem, minimize 3x1 plus 4x2 subject to 2x1 plus 3x2 greater than or equal to 8, 5x1 plus 2x2 greater than or equal to 12. So, the standard problem is a minimization problem with all greater than or equal to constraints. So, we first converted the inequalities to equations by adding the surplus variables or negative slack variables x3 and x4 to get 2x1 plus 3x2 minus x3 equal to 8, 5x1 plus 2x2 minus x4 equal to 12, and this give a contribution of 0. Now, we write the dual of this problem, because we have already seen that for a minimization problem with all greater than or equal to constraints here and strictly positive values, 0 0 is not basic feasible to the primal. So, this involved use of artificial variables or the two-phase method to solve this. Now, we are going to write the dual of this problem, and when we write the dual of this problem including the surplus variables, we get a dual like this: maximize 8y1 plus 12y2, which comes from 8y1 plus 12y2, two dual variables, subject to 2y1 plus 5y2 is less than or equal to 3, 3y1 plus 2y2 less than or equal to 4, y1 minus y1 less than or equal to 0, minus y2 less than or equal to 0, and y1 y2 unrestricted. Now, when we look at a dual like this, we quickly realize that 0 0, which is y1 equal to 0 and y2 equal to 0, is feasible to the dual. The way the dual is written, if the given problem is a minimization problem with all greater than or equal to constraints and strict positive coefficients here, then we will have a dual where 0 0 is feasible. So, we have identified a feasible solution to the dual. So, next thing we do is to apply complementary slackness to based on this feasible solution to the dual. So, if we look at 0 0, this is satisfied as an inequality, this is satisfied as an inequality, these two are satisfied as equations. So, with these two being satisfied as equations, we write the corresponding primal after applying complementary slackness conditions. Now, this corresponds to variable x3, this corresponds to variable x4. So, in the primal corresponding to this dual, after we apply complementary slackness, it is equivalent of solving minus x3 equal to 8 minus x4 equal to 12, because x3 and x4 are basic that comes out of this. So, minus x3 equal to 8 minus x4 equal to 12, we need to find a solution. Now, right now the solution for minus x3 equal to 8 and minus x4 equal to 12 is easy, but we also know that solving equations can also be done through linear programming. So, what we do is we rewrite this as minus x3 plus a1 equal to 8, minus x4 plus a2 equal to 12, a1 a2 greater than or equal to 0, x3 x4 greater than or equal to 0, and we minimize a1 plus a2. So, if this system has a solution also satisfying x3 x4 greater than or equal to 0, then it will automatically force a1 a2 to 0 and give us a solution with z equal to 0. If this does not have a solution, this plus x3 x4 greater than or equal to 0 does not have a solution, then one of the artificial variables a1 will be in the basis, and this will give us a z value which is non-zero, which is 1 or 2 depending on the number of a's that are in the solution. So, we solved this problem using the simplex algorithm here, and we found out that the solution a1 equal to 8, a2 equal to 12 with z equal to 20 is optimal. So, this gives a solution a1 equal to 8, a2 equal to 12, z equal to 20. Now, this problem is called the restricted primal. Restricted because it is restricted by the feasible solution to the dual. So, we apply complementary slackness and then we get the restricted primal. Now, the basic idea is this: if I have a feasible solution to the dual, I apply complementary slackness, and then if I solve the restricted primal, then the optimum solution to the restricted primal will be feasible to the original primal, and therefore it will be optimal to the primal and dual based on duality relationships. Because if there is a feasible solution to the dual, there is a feasible solution to the primal, and they satisfy complementary slackness, then they are optimal to primal and dual respectively. So, this method will start with a feasible solution to the dual, apply complementary slackness, create a restricted primal, and if the restricted primal is feasible, then it is optimal. Right now, the restricted primal is not feasible to this, because this gives a solution A1 equal to 8, A2 equal to 12, which is not feasible to this one. So, we need to get one more dual feasible solution. Now, in order to get one more dual feasible solution, what we do is we go back and then try to find out the dual of the restricted primal and see what happens. Now, when we look at the dual of the restricted primal, the dual of the restricted primal will now have two variables, in this case V1 and V2, and that will be to maximize 8 V1 plus 12 V2. The primal has two constraints, so the dual will have two variables which will be V1 and V2. So, this will be maximize 8 V1 plus V2. Now, as far as this is concerned, minus V1, x3 appears only here. So, minus V1, the coefficient is 0. Now, all values are greater than or equal to 0. So, the minimization problem, the maximization problem will have less than or equal to 0, minus V1 less than or equal to 0, minus V2 less than or equal to 0. From this appears only in the second constraint. From this, V1 greater than or equal to 1 and V2 greater than or equal to 1, because this variable appears only in the first constraint. So, V1 objective function coefficient is 1. So, V1 greater than or equal to 1 and V2 greater than or equal to 1, and V1 V2 unrestricted, V1 V2 unrestricted, because the two primal constraints are equations. Now, a solution to this is given by 1 comma 1, V1 is equal to 1 and V2 is equal to 1 with Z is equal to 20 or W is equal, the objective function value equal to 20. So, please note that this has an objective function value of 20, which is the same as the objective function value of 20 here. So, what we do is this we call as some V, which is the solution to the dual of the restricted primal. So, now we have a solution which we call here as Y, which was a starting dual solution. So, what we will do now is, now we want to create one more dual feasible solution and then apply complementary slackness and solve the restricted primal. So, let us now define the new dual feasible solution as Y dash, which we are going to have, and let us call this Y dash as Y plus theta V, where Y is the original 0 0, the existing dual solution, V is the solution of the dual of the restricted primal. So, V is 1 1 and we need to find out theta. So, if we need to find out theta, then we get another dual feasible solution to the dual, which is based on the original Y as well as V. Now, what do we want this Y dash to have? Obviously, when we started with Y equal to 0 0 and wrote its restricted primal and solved it, it turned out to be infeasible. Now, we want to define a Y dash which is feasible to the dual, whose restricted primal we will now come and solve. So, we obviously want the restricted primal to be different from this, because this is not giving us the solution. So, when will the restricted primal be different? It will be different when the new y dash satisfies at least one more new constraint as an equation, so that the corresponding variable will now enter into the basis here. So, theta should be such that at least one of the existing constraints which is satisfied as an inequality by y should now be satisfied as an equation by y dash, so that a new constraint is satisfied as an equation here, which means a new variable will appear here. It may replace an existing thing, but the only nice thing is that there will be one candidate which can come in as a basic variable here. So, which means theta should be made out of all those constraints which are currently satisfied as inequalities, so that one of those which are currently satisfied as inequalities will also become an equation. Second thing is that in general principles of linear programming, this by itself is infeasible, which is given by this, but this is a non-optimal solution to this. So, a non-optimal solution in principle should have a new variable that is entering, and if we relate the entering variable on the primal to the feasibility of the dual, then dual infeasible is primal non-optimal. Therefore, right now for all V that we have here, now this will satisfy V A less than or equal to C. So, we need a variable A such that we need a variable x j into this primal such that V A j is greater than 0. Now, this will satisfy the condition V A less than or equal to 0. So, we will look at those variables which have V A greater than 0, and we would like to look at these constraints which are right now satisfied as inequality, and then try and get the best value of theta. So, the best value of theta that we will have will be given by theta is equal to minimum of minus y a j minus c j V j greater than or equal to this. There is also a little more theory that is involved in trying to get this, but without getting into too much of theory, we have tried to explain this. This comes out of two things. One is we will consider only those j's which are satisfied as an inequality. They are not satisfied as an equation, because we want eventually one of them to be satisfied as an equation. So, we will not look at those that are right now satisfied as an equation. The second thing that I mentioned is we want V star A j greater than 0, because this will satisfy the condition V star A j less than or equal to 0. So, we want a new variable that enters which will have a V star A j greater than 0, which is in principle an infeasible dual at the moment, which will be a non-optimal primal, and such a variable will enter. Now, if we go back and check what is this. Now, this comes because if you look at this dual is of the form y a less than or equal to c. So, this is of the form y a j less than or equal to c j. comes from, for example, Aj's are the corresponding columns, Cj's are the objective functions, y is the dual variable. So, a dual constraint is typically of the form yaj less than or equal to Cj. Now, what we have written is we want y star is equal to y plus theta v. So, if there is a dual feasible solution y star or y dash, then y dash aj should be less than or equal to Cj. Now, y dash is written as y plus theta v. So, y plus theta v into aj is less than or equal to Cj. Now, y aj plus theta v aj is less than or equal to Cj. Now, we want finally to be an equation, so that one of these, as we said, will become an equation. So, for one of them to become an equation, just quickly change this inequality to an equation, and therefore theta will be of the form minus yaj minus Cj by v star aj, which is the same as Cj minus yaj by Vaj. So, basically this comes from this derivation that value which is the minimum will force one of these two to be an equation and the other would still be feasible. So, keeping that in mind, we write this expression for theta. Now, with the present solution, let us try and find out what we do. So, we first have to find out v star aj for these two. Now, v star aj from here, this is aj, which is the same as this. Now, v star is 1 comma 1. So, the value here is 2 plus 5 7, 3 plus 2 5. So, for both of them v star aj is positive. So, theta will be equal to minimum of minus yaj minus Cj. So, y is 0 0 right now, y is 0 0 that we have here. So, all yaj's are 0. So, minus of minus Cj is plus Cj. So, C1 is 3 by v star aj, we just now found out v star is 1 comma 1, aj is 2 5. So, v star aj is 7. So, minimum over 3 by 7 comma. For the second one here, this corresponds to the second coefficient. So, Cj is 4 by v star aj corresponding to this, v star is 1 comma 1, aj is 3 comma 2. So, v star aj is 5. So, theta will be minimum over 3 by 7, 4 by 5, v star aj greater than 0. So, theta is equal to 3 by 7. Now, when theta is equal to 3 by 7, y dash is equal to y plus theta v will be 0 0 plus 3 by 7 into 1 comma 1, which is 3 by 7 comma 3 by 7. So, now we have the new solution y1. So, we are going to say y is equal to 0 0 is what we started, y1 is y plus theta v, which is 3 by 7 comma 3 by 7. Now, if we look at 3 by 7 comma 3 by 7 and start substituting here, now this is 2 into 3 by 7 plus 5 into 3 by 7 is 7 into 3 by 7, which is 3. So, this is satisfied as an equation. Now, this one is satisfied as an equation. 3 into 3 by 7 is 9 by 7 plus 6 by 7, 15 by 7, satisfied as an inequality. y1 greater than or equal to 0, satisfied as an inequality. y2 greater than or equal to 0, satisfied as an inequality. So, this is the only one that is satisfied as an equation. So, this will force variable x1 into the basis. Now the basis is different, so we have to write the restricted primal. So the restricted primal becomes only variable x1 is there. So what we are trying to do is x1 alone is in the basis. So we are trying to solve here 2x1 is equal to 8, 5x1 is equal to 12 is what we are trying to solve. Now once again this is made into a linear programming problem with of course x1 greater than or equal to 0. So this will become 2x1 plus a1 is equal to 8, 5x1 plus a2 is equal to 12, a1 a2 greater than or equal to 0, and minimize a1 plus a2. So now we actually solve this linear programming problem once again by the it is like a two-phase method. We are essentially solving only this set of equations 2x1 equal to 8, 5x1 equal to 12, but we are actually solving it as a LP by adding two variables which may be like artificial variables with a +1 coefficient, and it is like a two-phase method to solve this LP. So we go back and solve this. We have x1, a1, a2. So a1, a2 will be the basic variables. So 2x1 plus a1 0, 8, 5x1 0, 1, 12. These have objective coefficients of 1, it is a minimization problem. These also have objective function coefficient of 1. So Cj minus Zj 0. So 1 into 2 plus 1 into 5 is 7. So 0 minus 7 is minus 7. You get 0 here, you get 0 here. So you get 20 here. So it is a minimization problem with a negative Cj minus Zj, the variable will enter the basis. So variable x1 will enter the basis. Now theta is computed as 8 by 2 is 4, 12 by 5. 12 by 5 is smaller than 4. So the variable a2 leaves the basis. This is the pivot element. So we do one more iteration with a1 and x1 coming here, Cj minus Zj, this is 0, this is 1, divide by the pivot element, 5 by 12, 0, sorry 1, 0, 1 by 5, 12 by 5, this minus 2 times this 0, 1, minus 2 by 5, 8 minus 24 by 5 is 16 by 5. So objective function value is 16 by 5, 0, 0, plus 2 by 5, 0, minus 2 by 5, 0, so minus 2 by 5, 1 minus minus 2 by 5 is 7 by 5, right. So this is Cj minus Zj, so no entering variable, algorithm terminates with the optimum solution. X1 is equal to 12 by 5, so the solution here is x1 is equal to 12 by 5, a1 is equal to 8 by 5, a1 is equal to 16 by 5, and z is equal to 16 by 5. Now the restricted primal has an optimum solution with an artificial variable still in the basis, and therefore the solution to the restricted primal is not feasible to this. So we need to do one more iteration here because it is not feasible to this. So, we will now go back and try to find out the dual of the restricted primal as we did. So, this restricted primal will have two dual variables V1 and V2, and the dual of the restricted primal will now have maximize 8 V1 plus 12 V2, which is the same here, 8 V1 plus 12 V2. This one is 2 V1 plus 5 V2. This constraint is 2 V1 plus 5 V2 is less than or equal to 0. So, 2 V1 plus 5 V2 corresponding to this is less than or equal to 0. Corresponding to this is V1 is less than or equal to 1, and corresponding to this V2 is less than or equal to 1. V1 V2 unrestricted in sign. So, we have this particular. So, 2 V1 plus 5 V2 less than or equal to 0, V1 less than or equal to 1, V2 less than or equal to 1. So, we have to solve this to try and get the optimum solution to this. We can either solve this by the simplex or we can solve this by the graphical method, because we have only two variables that are here. So, we will quickly try and solve it using the graphical method. And note that V1 V2 is unrestricted in sign. So, just solving it by the graphical method would give us V1 less than or equal to 1. This is say this is V1, this is V2. So, V1 less than or equal to 1 is here, V2 less than or equal to 1 is here, 2 V1 plus 5 V2 less than or equal to 0 is, this is one point, 0 comma 0 is another point, one point. The other point could be if V1 is equal to 1. So, if V2 is equal to 1, then V1 is equal to minus 5 by 2. So, V2 is equal to 1, which is here, V1 is equal to minus 5 by 2, this is 2, 2 and a half. So, this is another point. So, the third point will, the third line will look like this. So, this is 2 V1 plus 5 V2 less than or equal to 0. So, this is the feasible region, this is the region corresponding to this one, this is the region corresponding to this is the region corresponding to this. So, this will be the entire region that we will have. So, the objective function maximize 8 V1 plus 12 V2. Suppose we take 8 V1 plus 12 V2 equal to 24, then we have 3 comma 0 and 0 comma 2 that come here. So, this is 1, 2, 3 comma 0, 0 comma 2. So, the objective function line is like this. So, as it moves here, the last point that it will actually touch is V1 is equal to 1 and V2 is equal to minus 2 by 5. So, this will be the point, this is 0 0, this is V1 equal to 1. So, as it moves, this is the last point that which will come here. So, V1 is equal to 1, V2 is equal to minus 2 by 5. So, the optimum solution is V1 is equal to 1. So, V1 is equal to 1, V2 is minus 2 by 5. Now, note that the objective function value here, this is minus 24 by 5 plus 8, which is plus 16 by 5, which is exactly what we got here as plus 16 by 5. So, we now have a new V which is given by 1 and minus 2 by 5. Now we need to find out again a new value. First we need to find out theta, and then we also need to find out nu y dash is equal to y plus theta v. Now from this we know that this is the one that was satisfied as an equation. So all these three now become potential candidates to evaluate theta, and we also need to find out for which of them V star A is greater than 0. So we need to find out V star So first let us find out the second one, 3 comma 2. Now V star A is 3 into 1 minus 4 by 5, 3 minus 4 by 5 is 11 by 5. So V star A is greater than 0. So we will write minimum of for the variable x2 y a j minus c j. Y is 3 by 7, 3 by 7. So y a j is 9 by 7 plus 6 by 7, 15 by 7. Y a j is 15 by 7 minus c j minus 4, negative of that. So 4 minus 15 by 7 is 35 by 7. So 35 by 7 divided by y a j minus c j, y 1 is 3 by 7, 3 by 7. So 3 by 7 into 2 is 6 by 7, sorry 9 by 7 plus 6 by 7 is 15 by 7. So 4 minus 15 by 7 is 13 by 7. So this is 13 by 7 divided by V star a j we just now calculated as 3 into 1 3 minus 4 by 5, which is 11 by 5. So 13 by 7 divided by 11 by 5. Now for the third one here, which is variable x3. So this is variable x3 minus 1 0 into 1 minus 2 by 5. So V star a j is negative, minus 1 0 into 1 minus 2 by 5 is negative. Now for the fourth one, 0 minus 1 into 1 minus 2 by 5 is positive. So you get 2 by 5 here, and this is minus 3 by 7. So we get C minus y a j, 0 minus minus 3 by 7 is plus 3 by 7 divided by 0 minus 1, 1 minus 2 by 5, so plus 2 by 5. So 3 by 7 divided by 2 by 5. So this is minimum of 65 by 77, 13 by 7 into 5 by 11. So 65 by 77, the 3 by 7 into 5 by 2, which is 15 by 14. So you get 65 by 77 as the value. So now y dash is equal to y plus theta v. So y is 3 by 7, 3 by 7. So 3 by 7, 3 by 7 plus (65 by 77) into v, which is 1 and minus 2 by 5. So this is 3 by 7 plus 65 by 77, this is 33 65 plus 33 is 88, 88 by 77 is 8 by 7. This is 3 by 7, 65 into minus 2 by 77 into 5, this will go 13 times, minus 26 by 77, this is 33 by 77, so 7 by 77, which is 1 by 11. This is 65 into minus 2 by 5, minus 26 by 77, plus 33 by 77, 7 by 77, which is 1 by 11. Let us look at this. This is 33 plus 65, this is 11 times. So, 33 plus 65 is 98 by 77. So, 98 by 77 is 7 14s are 98, 14 by 11, 1 by 11. So, the value is 14 by 11 and 1 by 11. So, that is your y dash. So, we call that as y 2 equal to 14 by 11, 1 by 11. Now, we go back and check from this. Fourteen by 11, so this is 28 by 11 plus 5 by 11 is 33 by 11, which is equal to 3. So, satisfied as an equation. 42 by 11 plus 2 by 11 is 44 by 11, so satisfied as an equation. These are satisfied as an inequality. So, now we go back here and write the restricted primal. So, the restricted primal will become, now corresponding to these two, x1 and x2 will be the basic variables. So, we should solve for 2x1 plus 3x2 is equal to 8 and 5x1 plus 2x2 is equal to 12. So, in the same way we add two more variables, plus a1 equal to 8 plus a2 equal to 8, and then we minimize a1 plus a2 and say that a1 a2 x1 x2 greater than or equal to 0. So, one other thing is to solve it directly, the other is to go to the linear programming and do it. Since we have consistently been using the linear programming approach, we will do it using the same approach. So, we start with a1 and a2 as the basic variables. So, 2x1 plus 3x2 plus a1 is equal to 8, 5x1 plus 2x2 plus a2 is equal to 12. We have 1 and 1 here. So, we have Cj minus Zj. This is 2 plus 5 7. So, minus 7, minus 5, 0, 0 and 20. So, minimization problem. So, negative Cj minus Zj will enter. So, 8 divided by 2 is 4, 12 by 5. So, 12 by 5 leaves the basis. This is your pivot. So, you have a1 x1 coming in. Now, this is 1 and this is 0, 1, 2 by 5, 0, 1 by 5, 12 by 5, this minus 2 times this 0, 3 minus 4 by 5 is 11 by 5, 1 minus 2 by 5, 8 minus 24 by 5 is 16 by 5. Now, this is again Cj minus Zj, this is 0. This is minus 22 by 5, this goes. So, you get minus 22 by 5, this is 0, this is 1 plus 2 by 5, 7 by 5 and 16 Once again minimization problem. So, negative Cj minus Zj will enter. So, this enters. So, 16 by 5 divided by 11 by 5 is 16 by 11, 12 by 5 divided by 2 by 5 is 6, 16 by 11 leaves the basis. So, this is your new pivot. So, you will have x2 and x1 with 0 0 here, Cj minus Zj, divide by the pivot element 0 1 5 by 11 minus 2 by 11 16 by 11. This minus 2 by 5 times 1 is 0. So, 0 0 0 minus 2 by 5 into 5 by 11 is minus 2 by 11. So, this plus 2 by 5 into 2 by 11, this plus 4 by 55, 15 by 55 which is 3 by 11. This minus 2 by 5 into this. So, this is 12 by 5 minus 32 by 55. This is 12 into 11 is 132 minus 32 is 100 by 55 which is 20 by 11. So, this will be 0 0, this is all 0. So, you get 1, you get 1, you get 0. So, the restricted primal now has a solution which is x1 equal to 20 by 11, x2 equal to 16 by 11 with z is equal to 0. So, we can just quickly check 40 plus 48 is 88 by 11 which is 8, 100 plus 32 132 by 11 which is 12. So, now the restricted primal has an optimal solution with z equal to 0. So, the moment it has an optimal solution with z equal to 0, it means the artificial variables are not there in the solution, which means you have a solution based only on x1 x2. Therefore, this solution is feasible to this, right, which is 2 into 20 by 11 plus 3 into 16 by 11 is equal to 8 and so on. So, we get a feasible solution to this. So, right now we have a feasible solution to the dual, complementary slackness is satisfied. So, the corresponding restricted primal gives a solution that is feasible to the primal. Therefore, this solution is optimal to primal and dual respectively. So, the solution 20 by 11, 16 by 11 with z is equal to 3x1 plus 4x2, 3 into 20 by 11 plus 4 into 16 by 11. This is 20 plus 60, 60 plus 64 is 124 by 11, that is 3x1 plus 4x2. So, from here we get 14 by 11 into 3 is 14 8s are 112 plus 12 124 by 11. So, the solution 20 by 11 16 by 11 z equal to 124 by 11, which is what we got here 16 by 11 20 by 11 plus from the dual side 14 by 11 into 8 plus 12 into 1 by 11 gives the same. So, this is how the Primal-Dual algorithm works by giving us this optimal solution. So, the underlying principle is that for a certain type of problem which is like this, minimize, write the dual, work with a feasible solution to the dual, try to get a feasible solution to the primal by and if it is feasible then it is optimal. Otherwise, more importantly, otherwise try and get a new feasible solution to the dual such that there is at least one new candidate in the restricted primal. That is a fundamental principle, that there is at least one new candidate in the restricted primal. Once we start getting a new candidate in the restricted primal, the solution to the restricted primal becomes better. This theta also will ensure the dual feasibility is maintained. At the same time, a new inequality which is right now satisfied as an inequality will be satisfied as an equation. So, in this process of alternately updating these dual variables and then writing the restricted primal and solving it till the restricted primal has z equal to 0, which means it does not have artificial variables. This is the essence of the Primal-Dual algorithm. So, this is how the Primal-Dual algorithm works, and many a time we will be tempted to say that this algorithm is somewhat similar to the two-phase method. Now, instead of doing this, we could have straight away started with this problem, applied the two-phase simplex algorithm by simply adding two artificial variables a1, a2, giving them objective function values of 1, and in the first phase eliminating them and then proceeding to do that. So, computationally it is the same as the two-phase method, but it brings a very important idea that by making the dual different and by bringing a new candidate in the restricted primal, we can get to the optimum. In fact, the Primal-Dual algorithm is used extensively. The Hungarian method that we saw for the assignment is a direct application of the Primal-Dual algorithm. Now, let us take a very small example of an assignment problem and try to show how the Hungarian algorithm is actually a Primal-Dual algorithm. We will do that with a very small example here. So, let us look at a small 4 by 4 assignment problem. Now, let us do the row subtractions and simply write u1 equal to 2 with 0, 2, 4 and 6, u2 equal to 1, 0, 6, 4, 4, u3 equal to 2, 0, 1, 2, 3 and u4 equal to 6, 0, 2, 1, 2. Let us do the column subtractions. To get 0, 0, 0, 0, 2, 6, 1, 2, 4, 4, 1, 5, 0, 1, 3, 3, 1, 0, 4, 2, 1, 0. So, now we have u1 equal to 2, u2 equal to 1, u3 equal to 2, u4 equal to 6, v1 equal to 0, v2 equal to 1, v3 equal to 1, v4 equal to 2. Let us quickly make the assignment in this. Now, we realize that we can make an assignment here. This goes, this goes, this goes. Now, we can make an assignment here, and we could make an assignment in any one of them and say this goes. So, we have not been able to make 4 assignments. So, what we do is we do the line drawing procedure and get tick an unassigned row. If there is a 0, tick that column. There is an assignment, tick that row. Draw lines through unticked rows, ticked columns, and then change this such that if there are 2 lines, find the minimum theta, which is 1. If there are 2 lines, add theta. If there is 1 line, retain it. If there is no line, subtract theta. So, we get 0, 0, 2, 3, 0, 4, 2, 1, 1, 0, 1, 1, 1, 1, 0, 0. We know that whether we use this matrix or whether we use this matrix, the solution is the same. The reason the solution is the same comes from this. When we created this, we have written C dash ij equal to Cij minus ui plus Vj. By doing the row column subtraction, we have done this, and we have ensured that C dash ij is greater than or equal to 0. Therefore, this is dual feasible to the assignment problem, because the assignment problem constraint is of the form ui plus vj less than or equal to Cij. So, if we ensure that C dash ij is Cij minus ui plus vj is greater than or equal to 0, it means the dual is satisfied. Now, we satisfy complementary slackness only by assigning in 0 positions. We do not make an assignment in any other position. So, we satisfy complementary slackness, and if we get a primal feasible solution, then it is optimal. Right now, we do not have a primal feasible solution because we do not have 4 allocations. Now, what do we do next? By doing this, we actually readjust the ui's and the vj's. They are now adjusted again. This has a different u1, u2, u3, u4. In fact, here there is a line that goes, so v becomes minus theta. So, this is minus 1, 1, 1 and 2. Here, when there is no line, the theta actually reduces. So, u1 is equal to 1, u2 is equal to 0, this becomes 2, this becomes 6. No, this becomes, the theta gets adjusted here. So, when there is a line, theta remains the same. So, u4 is equal to 6, this is equal to 2. When there is no line, theta becomes plus 1, 3 and 2. So, for example, this 0 was 6 minus 6 plus 0 is 0, 6 minus 5 is 1. So, we still again have C dash ij equal to Cij minus ui plus vj. So, now what we have done is we have a new set of dual variables, but in the process what we have done is we have included at least one assignable new assignable 0. If you see carefully, this is one new assignable 0, which means this can bring one more variable into the primal basis. That is exactly what we did here. We started with a dual solution, and then after one iteration we computed a theta, and then we made sure that by moving from y to y1, at least one constraint which was originally satisfied as an inequality is now satisfied as an equation. So, here satisfying as an equation is reflected by a 0. So, at least one new constraint is satisfied as an equation, and the primal now has the opportunity to work with restricted primal works with one more additional basic variable. So, in that process we get the optimum. In a very similar manner, till we get the optimum, we keep making these ticks and subtractions till we finally get a feasible solution to the primal which would give us optimal. Here also, the moment we get a feasible solution to the primal, we get to the optimum. So, the Hungarian algorithm is a direct application of the Primal-Dual algorithm. So, once again the Primal-Dual algorithm starts with a minimization problem with greater than or equal to, writes a dual so that it is easy to find a feasible solution to the dual, then computes the restricted primal. If the restricted primal is feasible, then it is optimal. Otherwise, the y becomes y1 by carefully ensuring that there is at least one new dual constraint which is now satisfied as an equation. That is done by using this expression for theta such that dual feasibility is maintained and one new basic variable enters. Now, with that, once again the restricted primal is computed, and this process is repeated back and forth till the restricted primal is feasible, and the moment the restricted primal is feasible, it is optimal. And we have also seen now that the Hungarian algorithm is a direct application of the Primal-Dual method. So far in the course we have seen several aspects of linear programming. We started with the revised simplex algorithm, which essentially tries to quicken the simplex time taken per iteration. Then we saw how simplex is modified to handle bounded variables by treating them separately and not by treating them as explicit constraints. Then we looked at the idea of column generation through the cutting stock problem, where it is not necessary to store all the columns explicitly. Columns can be generated by solving subproblems, and we saw an application to the one dimensional cutting stock problem. Then we moved to the Danzig-Wolfe decomposition algorithm, where if the problem has a certain structure whereby removing certain constraints we can decompose it into smaller sized LPs, and then we exploited the fact that it is easier to solve a certain number of smaller LPs compared to solving one large LP, because the computational effort is cubic with respect to the number of constraints that we have. So, the decomposition algorithm taught us a way by which we can split a bigger problem into smaller problems, and by solving a series of smaller problems, and also by using the column generation idea, we generate entering columns into the basis. And then we have seen the Primal-Dual algorithm, where by intelligently working with the dual and by modifying the dual solution at each stage, and by solving a restricted primal, which is a much smaller sized problem, one can go back and get the optimum solution to the linear programming problem. So far we have seen several aspects of simplex algorithm and algorithms related and associated with simplex. We have largely looked at it from the point of view of making it faster by storing less and by generating entering columns as and when they have to be generated. So much we have seen about how to make the simplex better and handle enough variety. Now, the next thing that we may have to look at is, do linear programming or OR problems have only one objective, or can we have situations where these problems can have more than one objective or goal. So, from this we move to a topic called goal programming, whose basics we will see in the next lecture.